So in this section of implicit differentiation, let's first just go through a couple of different examples of what an implicit function looks like. What we've typically seen are functions that are written explicitly, meaning it's y equals. You can plug that into your calculator, y1, y2 equals this, equals that. Whereas implicit might look something like this. So what we're going to do in this section is learn how to derive these so we can still find slopes at tangent lines, but we're using a technique called implicit differentiation. So the first thing we need to do when we're thinking about implicit differentiation is we need to remember that we are treating y as a function of x. So if I'm deriving with respect to x, I need to treat y as a function of x. So let's see what that looks like side by side. So you'll notice here, I've written that f of x raised to the 7th, and then to the right, we have y raised to the 7th. We are treating y the same way we would treat that f of x. So if we were asked to derive both of those implicitly with respect to x, it would look like this. We would bring the 7 down, multiply that by, we keep that f inside, f of x now to the 6th power times f prime. Here's what that looks like when we derive y to the 7th with respect to x. We bring the 7 down, y is now raised to the 6th power, but we also include this dy dx. And that is the same meaning, that has the same meaning as that times f prime of x. So you'll notice also there are some books, and some of you may want to just write that as times y prime. And that's okay. It's just that if you are sloppy, oftentimes that prime gets lost in the sauce and you end up with something that looks different. I'm a dy dx. So let's see what this looks like in an equation. So you'll notice for question 1, they're asking us to implicitly compute dy dx. That just means find the slope, find the derivative to that equation x squared plus y squared equals 4. We know that's a circle. So I am deriving with respect to x. So if I'm taking the derivative of x squared, that is basic. It's 2x, right? Because it's with respect to x. However, if I'm now looking at y squared, I am implicitly deriving. So the derivative of y squared is 2y times dy dx. That is times the derivative of y. We're treating y as a function of x. And on the right side, derivative of 4 is 0. So you'll notice I'm still looking for dy dx. I still want to get dy dx by itself. That's the slope. So our next step is to subtract the 2x. And lastly, we divide by 2y and clean it up. So we end up with dy dx equaling negative x over y. So the biggest difference here, people, is that now that derivative doesn't just depend on x. So if I want to find the slope of the tangent line at some point, I'm going to need both the x and the y value to compute that. So let's look at the second part. They're asking us to find the slope of that graph at the 0.1 root 3. So that just means that I want the derivative at that point. So I plug them in. And that tells me that at the 0.1 root 3, my slope for the tangent line is going to be negative 1 over root 3. And I hope that makes sense to you, because at the 0.1 comma root 3, well, let's say that's like right around there. I don't know. But we know that that slope at that point is going to look like that. So it's negative. And then more specifically, it's negative 1 over root 3. So the good thing about this is we're finished. We kind of did what we needed to do. The more fun part is that they just get a little messier, right? So let's look at this example. We're implicitly deriving to find dy dx. So let's look at term 2. I'm still treating y as a function of x. So if I look at that circled term, if I'm going to derive that term, I need the product rule. So I know that my f is x squared. I know that my g is y. I know that f prime is 2x, and I know that g prime is dy dx, because the derivative of y is 1 times dy dx. We're always multiplying because we're treating y as a function of x. That's our chain rule. So here we go. So we start with g. So that's going to be g times f prime plus f times g prime. And it looks like that. Erasing. Now we're looking at the second term. We're going to derive that as well. So I know I can identify my f and my g. My f prime is 1, and my g prime is going to be 3y squared dy dx. So I'm adding that to my equation. So I get this. And the next part is more straightforward. Minus 3 equals 0. So you'll notice in this problem, I want all my dy dx's together. I want everything that doesn't have a dy dx over to the other side. So now things look like so. And feel free to pause and take a look just to see. I just rearranged some things because I like my x to go before my y. So if we're looking at the left side, what do they both have in common? That's right, a dy dx. So what am I going to do? I'm going to factor it out. So it looks like this. And the last thing is, I want to get it by itself. So we divide by x squared plus 3xy squared, and our answer cleans up to this. So we're going to notice that not everything is written as dy dx. You're not always wanting to derive with respect to x. There are going to be times where we want to derive specifically with respect to t. So we're going to do a lot of problems that are all with respect to time. That WRT means with respect to. So let's look at that equation. This is an ellipse. X squared plus 5y squared equals 36. And part A is asking us to differentiate this all with respect to t. So, folks, that means I need to treat y as a function of t, and I need to treat x as a function of t. Let's do this. So, the first thing is x squared. What is the derivative of x squared? That's going to be 2x times dx dt, because now I'm thinking of x as a function of t. So, same thing goes for 5y squared. What's the derivative of 5y squared? Well, that notation is 10y times dy dt. Remember, the dy dt, derivative of y with respect to t. Dx dt, derivative of x with respect to t. Equals 0. Perfect. So we're asked in this problem to isolate dy dx. So we're moving everything over and dividing. And that would clean up to give us that. So you'll notice now in that problem, we're suggesting that dy dt, the rate of change of y with respect to t, depends on not just x and not just y, because it depends on x and y, but it also depends on the rate of change of x with respect to t. Then they'll just ask you, or you're going to find dy dt when, and they'll give you specific values. It's a plug and chug. So it looks like that, and then we can either leave our answer like so or clean it up, and we get -2. So let's just do a couple more examples of this. So here we're going to find dy dx at that given point, 1, -1. So I'm going to just work through my product rule for the first one. So we've got that, and now if we're plugging in our product rule, we end up with that. That's our g f prime plus f, which is -4x cubed g prime. And then we keep going. So the derivative of, I'm here now, 5y cubed is going to be -15y squared times dy dx, because I'm deriving with respect to x. Derivative of 4 is 0 equals 5. I only have one term that has a dy dx. No, I don't. I have two terms that have dy dx, so I want to get those two by themselves. And I end up with this. And now we're going to factor out that dy dx from both terms to give us this, and then we divide by the change. Perfect. And lastly, we want to plug in 1, -1 for x and y, which looks like that. And I think our last step is just cleaning it up, and we get this. What a mess. The next example that I want to do is where we need to find the second derivative of an implicit function. So here we go. So we know how to derive these now. So we'd end up with this step as our first derivation, and then we're going to get dy dx by itself. So our dy dx looks like that. So then the next part is I want to take the second derivative. So I'm going to derive that equation. And I'm hoping that you're identifying that when I do so, this on the left side now becomes that notation. This is saying now the second derivative, if I took the derivative of that left side, is going to be this. The right side, well, we're going to need to use the quotient rule. So let's identify what f and g and f prime and g prime are. So we see we've got our f, our g, our f prime, and g prime. So let's plug that into our quotient rule. So it looks like that. Now what? Now I just need to clean up one thing. I can't have this notation in my second derivative, so I need to replace dy dx with what it equals in terms of x and y. What does it equal in terms of x and y? That. So our step now looks like this, and that's our second derivative. I am not going to waste your time cleaning that up because it didn't ask us to, so we would just box that answer. So the last problem we're going to do is a free response question from the AP. I forget what year. So anyway, so we are given in this that a cylindrical barrel with a diameter of 2 feet contains collected rainwater, like so, and the water drains out through a valve at the bottom of the barrel. The rate of change of the height of the water barrel with respect to time is modeled by this. That is the rate of change of height with respect to time. Height is measured in feet. Time is measured in seconds. They always give you geometry equations, so you don't need to have memorized volumes of spheres and cylinders and whatnot. All right, so here we go. Find the rate of change. So I'm on A. Find the rate of change of the volume of the water with respect to time. People, that is asking us to find dV dt. Find dV dt when the height of the water is 4. So we want to find dV dt when we know the height is 4. Now, here's something that might prove to be pretty useful. That equation of volume equals pi r squared h. Let's look at that r in that problem. Is my r going to change? No. It's a cylinder and my r is constant. What's the radius of that cylinder? 1. So I can rewrite that equation actually as pi times 1 squared h, or just pi h. So if I'm asked to find the derivative of v with respect to t, that means I am deriving all of those variables that aren't t implicitly. So that would leave us with pi times, what's the derivative of h with respect to t? dh dt. Right? Derivative of h is 1 times dh dt. So now we write that as pi times, what is dh dt? Oh, it's -1/10 times root h. And what did they tell us our h was? 4. So, sorry, I had to move up to C. So then that gives us as our answer -pi/10 times root 4. I can leave my answer like that, but I want to clean it up a little bit. So then that gives us negative pi over 5. I'm not finished. I need units. Volume is cubic feet, and our time was in seconds. So this would be cubic feet per second. So our dv dt is going to be negative pi over 5 cubic feet per second. So let's look at B. Now they're telling us when h is 3, is the rate of change of height of water, that's dh dt, is dh dt with respect to time increasing or decreasing? So what do I need to figure out whether or not dh dt is increasing or decreasing? I need to find the second derivative, because if I know that my second derivative is positive, it's going to be increasing. If my second derivative is negative, it's going to be decreasing. So let's do it. So our dh dt equation is this. So let's take that derivative. So you'll notice when I did that derivative, we've got the constant, the negative 1/10, and the derivative of h to the 1/2 is 1/2 h to the negative 1/2 times dh dt, implicit. So now that I'm at this part, I then want to go back and say, well, what is dh dt? So then I replace dh dt with what it equaled, this. And so, folks, this now cleans up to give us 1 over 200. And our answer would then read, since our second derivative is always positive, it's at constant, negative 1 over 200, we know that that rate of change in the height when our h was 3 is increasing because our second derivative is positive.